Welcome back. So in my previous videos, we already introduced and kind of derived the power rule for integrals. So I'm going to write the power rule for integrals here. And then we also want to derive it and see if it works through a different type of a proof. Okay. So we already know that the power rule for integral looks like this. The integral of x to the power n dx is x to the power n plus 1 over n plus 1, and then there's a plus c, a constant there. Okay. So, and we also at the same time understand the fact that the antiderivatives or integrals is the reverse process of the derivatives. So what does that mean in terms of the derivatives? If the integral of this function x to the power n is this side, then the derivative of this side should be x to the power n. Okay. If that is true, then we can convince ourselves that yes, this identity or this integral power rule holds true. Okay, guys, we were able to see that from a pattern and few different ways. Now let us also look at this from just directly finding or evaluating the derivative of the right hand side and see if the derivative of the right hand side actually equals to this x to the power n. Okay, so let us start by the right hand side with the right hand side here and try to find the derivative of this function. So we're trying to find the d over dx of this function x to the power n plus 1. Guys, it may look like a complex function, but it is not too complicated. Once we start doing it, you will see that it's not too complicated. So obviously this is going to be like derivative of the first piece plus the derivative of the second piece. So derivative of the first piece, d over dx of this x to the power n plus 1 over n plus 1, and then derivative of the constant with respect to x. So guys, here what we can do is we can just take out this 1 over n plus 1 outside, and then it's just the derivative. Guys, I like to write all the steps, and I highly recommend everybody to write those steps. Okay, and we know the derivative of a constant is simply 0. We don't have to worry about this. Okay, and now moving on here, this 1 over n plus 1 stays outside. No need to worry about that. Here I got to use the power rule for x to the power n plus 1. We know the power rule for the derivatives. It is simply bring in the exponent up front, and then you reduce the exponent by 1. And that's all you have to do for the power rule and for the derivative of this function. Here you can easily see that this guy and this guy is going to cross out the same terms, and then you are left with x to the power, well, 1 and 1 will cross out, x to the power n. That is the function that we started with for the integral of that function. So from this also, finding the derivative of the right hand side, it gives me back the x to the power n, which is also thought of as an integrand, and that implies that this actually holds true, that the integral of x to the power n dx is in fact equal to x to the power n plus 1 over n plus 1 plus c. Okay. So since we know, or we knew that the antiderivative is the reverse process of a derivative, so we were able to find the derivative of the right hand side, and we get that equal to this function x to the n. From that also we can conclude or we can justify that the integral or this power rule actually holds true. So guys, we looked at several different ways of writing the power rule or actually verifying the power rule. So now we know the power rule. We're going to start using power rule on examples, but there's keep in mind, of course, there's this criteria here, or this thing that n cannot be equal to -1, and we can see that directly from looking at the denominator. Like we're going to get into trouble of dividing by 0. So for n equals to -1, we have a different formula. Guys, I'm going to write some of these other formulas in my next video, and I'll probably prove or verify some of these based on the same idea that the derivative of the right hand side has to be equal to the this function on the left hand side. Okay, and then we'll use these things to solve examples.